I'm going to walk through the solution to this practice problem. Hopefully, you've had a chance to review it and try it yourself. If not, just pause and give it a try. So, in this one, we're going to compare the solubility of oxygen in freshwater lake at sea level and at then Echo Lake in Colorado, where it'll be at an elevation of 10,000 feet. We've been given some data. We're going to use that to calculate the change in solubility of oxygen just by increasing its altitude. So the equation we're going to use is that Henry's law. So we know that our solubility of oxygen is going to be equal to Henry's constant times the partial pressure of oxygen. Now we want to get the change in solubility. So we really know that we need to look at the difference between the solubility of oxygen at one elevation versus another. So we can say at sea level, it's a bad level, minus it at 10,000 feet. And we'll take the absolute value of this. All right. So we've been given Henry's constant for oxygen. We've also been given the partial pressure of oxygen at two different altitudes, at sea level and at 10,000 feet. So I'm going to use this information to calculate my solubility at each of those altitudes. So my solubility at sea level is going to be equal to that Henry's constant. So it's 1.3 times 10 to the negative third molar per atmosphere times that partial pressure, which is the 0.21. So this is what we just did in our example problem. Now at 10,000 feet, our solubility of oxygen should, as we go up in altitude, our pressure decreases. It should drop. And it does. It goes down to 0.14. So we're still using the same Henry's law constant because we're going to keep temperature the same between these two or in our comparison and just change our atmosphere or our pressure. And that'll be 0.14 atmospheres. So this is set up to calculate the solubility for both of these altitudes. I'm just going to plug this into my calculator at this point. I'm going to get for my sea level what I just did, which was 2.73 times 10 to the negative 4 molar. And then for my 10,000 feet elevation, I'm going to get 1.82 times 10 to the negative 4 molar. And so those are my two solubilities. So to get the actual change in solubility, I'm going to look at the difference between them. Now let's calculate the difference in our solubility. I'm still going to, it depends on how the problem is worded, right? I'm going to do the absolute value because it just wants to know what's the change. It doesn't say if I need to say if it's decreasing or increasing, but I can also give that information. Typically, when I look at the change in something, it's the final minus the initial. So I'm going to do my final solubility minus our initial solubility. But then that depends on whether or not you're increasing, like you're going from sea level up to Colorado, or if you're going from Colorado down to like sea level. So hence the absolute value sign. But anyway, if I interpret this to be 10,000 feet down to as final and my initial is at sea level, then I'm going to have my 1.82 times 10 to the negative fourth molarity minus the 2.73 times 10 to the negative fourth molarity. Take that absolute value. I'm going to get a value that's negative 9.1 times 10 to the negative fifth molarity. So that means it's going to decrease the solubility as we go from sea level up to 10,000 feet elevation. You could just also report this as a change of 9.1 times 10 to the negative fifth.